In a previous video, we talked about how to find relative maximums or minimums. Here, we're going to talk about absolute extrema. So what this is some of our relative maximum and minimums, they weren't just the biggest or the smallest in their sort of neighborhood, but they were actually the biggest or the smallest overall for the entire domain. This is what we think of when we think of absolute extrema. So let's start with an example. So consider the graph below. So let's first find the relative maximums and minimums for this graph. Okay, so we're going to have a relative maximum. So we want to think, where's the graph the biggest? So that's going to be this little peak right here. So at 0, so there's a relative max of y equals 0, which happens at x equals 0. So remember, the relative maximums are the y values. There's a couple of relative minimums. Okay, so we have this minimum over here. So there's like a little valley here, and this is the bottom. I've estimated these numbers for you. So this is going to be y is negative 1.78, which happens when x is negative 2. And then there's this other one, y equals negative 5.25, which happens at x equals 3. Okay, so those are the relative maximums and minimums for this graph. Now, we can see that this minimum here happens to be the smallest. This is the smallest y value of the entire graph, right? For the rest of the graph is all entirely above that y value. So this is actually an absolute extrema. Okay, so we would call this point here an absolute or global minimum. Okay, so we have this absolute min. Again, it's still the y values, so it's of y equals negative 5.25, which again occurs at x equals 3. And there's no absolute max. And this is actually because if we think about the limits as we go to the endpoints of the domain, which here is plus or minus infinity of our function, the graph gets really big. So it's approaching positive infinity, so there's no way to have a maximum value. So let's define these more formally. So if f is a function defined on some interval and c is a number in that interval, then we say f of c, which again, remember, this is the y value. Okay, f of c is the absolute maximum of f on the interval if f of c is bigger than all the other f of x's. So f of c is greater than or equal to f of x for all x in the interval. Okay, so not just in its neighborhood, but in fact on the entire interval. And again, we would say f of c is an absolute minimum if it's the smallest. So f of c is less than or equal to f of x for all x in the interval. Okay, so let's look at another example. So suppose we have these two graphs here. So we're going to start on the left one. So we want to find the absolute extrema. Okay, so is there an absolute max and an absolute min for each? Okay, if you prefer to use the word global, that's fine. They're interchangeable. Okay, so we want to look at this graph. We want to think, so it's defined on this interval. So we're not talking in a neighborhood, we're talking this entire interval. So from x equals negative 4 to x equals 3. What is the biggest y value? Well, we can see in this first one that it gets up to y equals 5. Okay, so that's going to be our absolute maximum. So it's y equals 5, which happens at x equals negative 2. Okay, what about the absolute minimum? Okay, well that occurs at this valley here, so the smallest part, so that's going to be y equals -4, which is when x equals 1. Okay, now notice, what do x equals 2, -2, sorry, and x equals 1 have in common? Well, they're both critical numbers. Okay, and that makes sense because these maxes and mins occur at the peaks and at the valleys, which these both have slope of 0, right? So they're going to be critical numbers. Just as the relative maxes and mins occurred at the critical numbers, we're going to have something similar happening here. Okay, what about this other graph? So again, we want the absolute max and the absolute min. So let's do the minimum first. So it looks like the smallest it gets is at this valley here, so it's going to again be -4, and again it's at x equals 1. Okay, so that's the absolute minimum. For the maximum, it actually occurs here, right? This is the biggest y value that we get to, which is actually y equals 3, which occurs at x equals -4. So again, okay, this x equals 1, this is a critical number, but this x equals -4 is not a critical number. It's actually an endpoint of our interval. Okay, so if you imagine the graph keep going, you wouldn't expect at -4 there be a critical number unless it's a sharp turn, maybe, the way that it looks. Okay, so this is the idea behind the extreme value theorem. So sometimes, or often, just like the intermediate value theorem, we denote this EVT. Okay, so the extreme value theorem. So what it says, and there's a couple things that are important here. So if f is continuous, okay, continuous is important, continuous on a closed interval. Okay, both of these statements are important. So the closed interval from A to B, then we're definitely, f is going to have an absolute maximum and an absolute minimum. Okay, so notice in these two, the functions are continuous, and it's defined on a closed interval, -4 to 3. And we got maxes and mins for both. In this first one we did, it's continuous, but it's not defined on a closed interval. And notice that we had an absolute minimum, but we did not have an absolute maximum. Okay, so what this theorem says is if you're continuous on a closed interval, you're definitely going to have both an absolute maximum and an absolute minimum. Okay, now a few notes. So unlike relative extrema, a function only has one absolute maximum minimum value. Okay, so because it's the biggest y value that occurs, or the smallest y value that occurs, there can't be multiple different values. But it could occur in more than one place. Okay, so there's only one, but it could occur multiple times. So I'll give you a picture of what that might look like. Okay, so let's say these are my axes. My graph might look something like that. Okay, and maybe these points here are the same y value. Okay, so then you get the same maximum, it just occurs in more than one spot. Okay, so this would occur at x1 and at x2. Okay, but it's the same y value, so the maximum is the same. Okay, so why is the closed interval important? Okay, well we could have something like Okay, so let's say we have an open interval from A, maybe it doesn't really matter, let's just leave it, A to B. Okay, but maybe it's only closed on one side. So maybe it looks like that. Okay, maybe this is at 2 and this is at 5. Okay, so here we would have a absolute or global minimum of y equals 2 at x equals a, so at the endpoint, but we would not have an absolute maximum. Okay, so the limit as we approach b from the left here of our function, it's going to 5, but it never reaches 5. So remember, that means we can get as close to 5 as we want, which means that there's no biggest value because we don't actually get to 5. Okay, so in order to guarantee that there's both a min and a max, you must have this closed interval. Now, is it possible that you don't have a closed, you have an open interval and you get a max and min? Yeah, of course it's possible. But you can't guarantee that it's always going to happen unless you have a closed interval and your function's continuous. Okay, so it's possible that you still have a max or min even if you have an open interval and you're not continuous, but it's not always going to happen. So I'm giving you an example of where it doesn't. Okay, so the continuous requirement is important. Okay, so you might have something like, so maybe you do have a closed interval. Okay, so again, maybe you're going from A to B, but your function might do something crazy like this. Okay, where this is at, say, C. Okay, so if there's a jump, even though this is defined on the entire interval from A, the entire closed interval from A to B, there's going to be no maximum because of the jump. Okay, we're going to approach whatever the y value is here, but never reach it. Okay, you could also have something like not continuous. Maybe you have an asymptote in your interval. Okay, so maybe it's well, here it wouldn't, now you wouldn't have a closed interval. Okay, but you might have something like okay, so now you're not continuous and you don't have a closed interval. You still have a maximum, which is whatever the y value is at x equals a, but there's going to be no absolute min. Okay, so these are places these are examples of where it goes wrong. But we can't use the extreme value theorem here because we did not meet these two important conditions. So the yellow condition that you're continuous, and or the pink condition that you have a closed interval. So when you do meet those conditions, then it's easy to find the extrema because you know that they exist. Okay, and you know, well, we know they're going to occur at critical numbers or at the endpoints of your interval. Okay, so this is how we're going to find the absolute extrema on a closed interval when our function's continuous on that interval. So the first thing we do is we find the critical numbers. So we find the critical numbers of f, and we only care about the ones that are in our interval. Okay, so if you get some that are not in the interval, just throw them away. Okay, so what we're going to do here is find C such that f prime of c is 0, or f prime of c does not exist, and c is between a and b. Okay, so we only want the ones in our interval. Okay, and then what we're going to do is we're going to evaluate our function f at each critical number that we found in the interval. Okay, so you're going to take each of the c's that you found, and you're going to find the y values. Okay, and then you're also going to evaluate at the endpoints. Okay, so you're going to find f of a and f of b. So the y values for those, and then you just compare them. Okay, so the largest y value in step 2 or 3 is the absolute max, or global max, and the smallest in each of those steps is the absolute min. Okay, so that's what we're going to do. So we don't even have to think about whether they're maxes or mins. We just need to compare. These are the only places. So the critical numbers in our interval and the endpoints are the only places where we could have an absolute extrema. So all we need to do is figure out which of them has the biggest y value. Okay, so let's do an example. So we have our interval from -1 to 8, and our function is x to the 8/3 minus 16x to the 2/3. Okay, so the first thing we want to do, let's just make sure that it's continuous. Okay, so we want to think about the domain. Because my exponent has a rational exponent has a odd number in the bottom, I'm doing an odd root, which means I can evaluate this for every x. Okay, so the domain here is -infinity to infinity, and it's continuous everywhere. So it's definitely continuous on the interval from -1 to 8. Okay, so what that means is the extreme value theorem applies. So we have a closed interval, okay, and we're continuous on that interval. So we know that there's going to be a max or min. Okay, so the extreme value theorem guarantees both an absolute max and min. So now we want to find them. So the first thing we want to do is find the critical numbers. So we take the derivative. So it's going to be 8/3 x to the 5/3 minus 16 times 2/3 x to the -1/3. Okay, so if I simplify this, this is 8/3 x to the 5/3 minus 32/3 x to the 1/3. Okay, maybe actually I'm going to write this first one a bit different. Put it as a fraction. So it's 8x to the 5/3 over 3. So I want to make a common denominator, so I'm going to multiply this first one by x to the 1/3 over x to the 1/3. Okay, so what that's going to give me is f prime of x is 8 x squared, actually, minus 32 all over 3x to the 1/3. Okay, and then if I pull out the 8, just to make things a bit nicer, it's x squared minus 4 on the top. Okay, so that's my derivative. So now I want to find its critical numbers. So if f prime of x equals 0, that's when the top is 0 of my derivative. Okay, so that's when I can factor this. This is a difference of squares. So x minus 2, x plus 2 is equal to 0. So I get x equals 2 and negative 2. Okay, those are critical numbers. Now, my interval's from -1 to 8. So let's get rid of that one because it's not in my interval. Okay, so I don't actually need that one. It is a critical number for the function, but it's not in my interval, so it doesn't matter. So we just get x equals 2 there, and then we need where does the derivative not exist, because those could be critical numbers. That's when the bottom equals 0, which is going to be at x equals 0, which is in my interval. Okay, so I get these two critical numbers. Okay, now what I like to do, I'm going to do steps 2 and 3 at the same time. I'm going to make a table. Okay, so I have my x values that are important. Okay, and then I want to find my y values for each. Okay, so I put my, we'll put the critical numbers in. So x equals 0. Okay, so then y is going to be, so now I have to go to my original function. So this is, well, okay, y is going to be 0 here because that one's easy to do. And then when I have x equals 2, y is going to be 2 to the 8/3 minus 16 times 2 to the 2/3. Okay, this is not a nice number. Okay, but if you compute it, it's approximately negative 19.05. Okay, so these are my critical numbers that are in the interval. Okay, but I also want to check the endpoints. So that means I also have to plug in x equals -1. So y is going to be -1 to the 8/3 minus 16 times -1 to the 2/3. So that's actually going to be +1 minus 16, so that's going to be -15. Okay, and then I have to do the other endpoint, which is x equals 8. So I get 8 to the 5/3 minus 16 times 8 to the 2/3. And this is actually going to be 192 because it's 2 to the 5. Does that make sense? 2 to the 5 minus 16. Oh, it's not 5/3. Sorry, that's why. Okay, I was worried it didn't seem right, but it's because I made a typo here. It's actually 8 to the 8/3. 5/3 was the derivative. Okay, so it's going to be 192. So this, in these two parts, we're checking our endpoints. Okay, and then we just want to look for the biggest and smallest values. Okay, so the biggest value obviously is this 192. Okay, so that means that our absolute maximum is y equals 192, which occurs at x equals 8 at an endpoint. And the absolute minimum is this negative 19.051. So it's y, oops, I missed the is approximately, I mean, you could actually compute, it's going to have to do with cube roots of 2. Okay, I'm just going to make it approximate because it doesn't look like a nice number, but negative 19.05. and this is when x equals 2. So this one's at a critical number for the graph. Okay, but on that interval, that's the biggest and the smallest values. So you don't have to do much thinking. Find the critical numbers, evaluate them, so find their y values, and then compare those to the y values of the endpoints. The biggest one is your maximum, the smallest one is your minimum. There's one other theorem here that we can make use of that's useful when we're doing applications. And in particular, if you don't satisfy the extreme value theorem. So if you have a function that is continuous on some interval, okay, notice that it doesn't have to be closed, and it has exactly one critical number, okay, c, that's in the interval, then if you know the relative max, if you know the sort of the classification of c, that's actually going to be the absolute extrema. Okay, so if f has a relative maximum at x equals c, then f has a absolute maximum at x equals c. Okay, so I guess another way to say this is f of c is an absolute max. Okay, so what's going on here is you have some interval. Okay, let's say it goes from A to B, and you have some critical number C. Okay, so if you know that C is a okay, something like this, so it's a relative maximum. Because there's no other places the function can change, even if these are open, it doesn't matter. It has to actually be the absolute, because it has to, on your interval, it has to increase to C and then decrease after C. Because it's the only critical number in the interval, there's no other place where it could change. And it's continuous, I should say. So it's continuous, so there's no vertical asymptote or anything like that in the interval. And it's the only critical number, that's the only place it can switch from increasing to decreasing. So it's a relative maximum, it actually has to be the absolute maximum. Similarly, if it's a relative minimum at C, then it has to be, so then f of C is actually, I guess I could say, instead of an, I could say the absolute minimum on the interval. Okay, and then so I'm going to do another picture here. Okay, this time I'm going to make C does not exist critical number. Okay, so maybe C is over here. So you might have something like that. Okay, and again, maybe these are open, maybe they're closed, it doesn't actually matter. So here it's going to decrease to C and then increase from C. Because C is the only place it can change, it actually has to be, if it's a relative min, it has to be the absolute min.